Okay, it's Wednesday, July 19, 2023, and we have Dr. Adrian Marsh, who's going to be explaining what we have in front of the table here.
Okay, so this is a presentation that Eric Dollard and I'm going to do. It's just after the ESTC 2023 conference, and we've stayed after to do some special work that actually hasn't been done for a very long time before. So we're going to be going into cathode modulation. We've seen over the conference, I gave a presentation on the golden ratio discharge, and there we used an AM modulated power supply to produce the golden ratio discharge. Now that's one way of doing it. Another way of doing it is direct cathode keying or cathode modulation, and Eric has built and designed a suitable cathode modulator, which is part of the RF rack. I'll be asking him to go through that in more detail in a minute. So let's just have a look at what we've got on the bench here. It's actually a very similar setup to what we used in the conference. So starting from the coil, this is the coil that we've used for the golden ratio discharge. It was one that I designed and put together in my lab in the UK, and we built a similar set here for Aaron's laboratories. So it is a straightforward Tesla coil. It's not specially designed in any way other than the frequency that we want to operate. It has no golden ratio features in it. It wasn't designed that way. It was just designed to have a very high voltage inversion. So in other words, it's good for making large discharges. So it's a two-coil system with a secondary coil. We have a primary coil, and we are powering it as a Class C Armstrong oscillator. So we have a feedback coil here. That feedback coil goes back to the grid, and then we run it from our generator. I'll go into that in a minute. So we have a tank circuit consisting of this KP14 Russian vacuum variable capacitor. That's a 10 kilovolt, 1000 picofarad capacitor. That's connected directly to our primary coil in a parallel circuit. So if we were to do an analysis of that, we would have a fundamental series mode in around about 3 megacycles, and we have a lower parallel mode at around 2.8 megacycles, and we have a upper parallel mode at around 3.2 megacycles, and we will be operating this in a frequency band around about 2.5 to about 3.4 megacycles. That is connected to a single tube. This is a power triode. It's a GU-5B Russian military, and as Eric and I found out, this just wants to oscillate. It just wants to oscillate all of the time. So Eric even said you put a 9-volt battery on, that's probably going to oscillate. So it's very good as a power oscillator. It has a 2.5 kilowatt maximum plate dissipation, 5 kilovolt anode maximum potential, but we've found it's a very robust tube, so it can go to higher anode voltage and can run to quite high efficiency if it's properly set up. So this is the generator unit. We can see that we're connected here with iron wire, and Eric's going to go into more detail why that is a little bit later. We have various meters on here that allow us to measure the average plate current here between our generator and our power supply, and we also can measure the grid current as well. We also, on the front of this unit, where you can't see there, we can also measure the filament voltage and current, and we can measure the high voltage that's coming from our plate supply. So previously, as I said, we were using the amplitude modulated high voltage unit, but this time we have connected here, we have connected this RF rack high voltage supply. That's a DC supply at around 4800 volts. So also we have a pickup coil here. Because we are using this as a power oscillator, we need to have a feedback coil, so that picks up a little bit of the flux coming off of the coil, feeds that back to the tube and forms a positive feedback for a power oscillator. So the whole unit represents about a 4 kilowatt power oscillator, and that can be used for a very wide range of experiments, as we're going to demonstrate. So we will start with the burning bush, and then we will move on to a whole different set of characteristics that you can get when you cathode modulate this. But first of all, I'm going to hand over to Eric to talk about what we've got on the high voltage supply, and then talk about parasitic oscillations in systems like this.
So this is our rectifier and rectifier control panel. So the high voltage DC supply for the vacuum tube is down in this lower section, and then the controls for it are up here. So this is basically a 4,000 volt 1/2 amp or 2,000 volt 1 amp DC power supply, which is to be selected by a switch, but now we're still using the patch panel, which is an easier way to do it. This is also capable of being connected to the modulator for AM, so the power supply has a superimposed alternating current signal on top of it, representing the music or tones or what have you. And then the other unit, which is in a state of finalization, is the grid control unit for the power amplifier. Power amplifier is not done, so that's why we're using this oscillator. There's a lot of complications with using an oscillator, but at any rate, there's also a lot of complications with building a power amplifier from scratch. So this is basically the control unit for the amplifier. It's called the grid control panel. It has the tuning unit to take the RF from the exciter and feed it to the grids of the tubes. That's this part here. Then it has the DC power supply for running relays and all the stuff in the power amplifier and power unit. And then we have the choice of either going from amplitude modulation into the cathode of the tube, or cathode rectangular wave keying with either a Morse code or relays or whatever. And then we also have the linear AM mode here, so that we can feed the feedback into the cathode from the voltage sensing of the modulator, the second harmonic component, which controls the size of the flame. Or we can go over here, and then it's rectangular wave modulation with a bank of relays. And so that's what we're going to do now. So when this switch is up, basically we get the burning bush because there's no external modulation coming in, so it's just carrier. And I put the switch down here, and now the cathodes of the tubes are keyed. In this case, it's the cathode of that tube, not the tubes in here. And then we have this little China box here that makes our pulse waveform, which then will be amplified immensely and appear as an outburst on the high-frequency terminal.
And what kind of rate are we modulating at on that box?
I think it's 1/10. The pulse repetition rate is 10 pulses per second, and the pulse width is 1/10 of a second.
Okay.
Somewhere around there, or maybe
it's about 10%. Yeah.
Yeah, it was about 10%.
Okay, good. And so there are two modes that we can do this in. So obviously we'll get the burning bush first of all, and then we're going to switch on the modulation. So let's do an initial run, and then later we will come back to talk about how to set this system up and the difficulties that we had along the way of making this work well. But let's first of all do a demonstration, because everybody wants to see the sparks. Okay, so what we're going to do, we're going to do the demonstration now, and we're going to go through a process. Obviously, we have to tune this properly, so before we can increase the size of the discharge. So that involves quickly turning on the high voltage and looking at the plate current, looking at the grid current, make sure everything is in the right envelope for the tube, and then we may have to do some kind of tuning mechanism both on the primary tank circuit and on the grid leakage feedback bias. So Eric, if you'd like to turn on. Okay, so this is now the burning bush. We're first of all going to check our characteristics to see where we're operating. So we've currently got about 500 milliamps plate current at average current, and we've got about 80 to 90 milliamps average grid current. And we want to get everything so it settles down nice and stably. Ideally, we want to tune away the chirps and the crackling, which is...
I'm going to let the tube cool down a bit.
Sorry?
I'm going to let the tube cool down a bit.
Okay, yes. Because of the airflow rate, this tube requires a very high airflow rate. It's around about 220 cubic foot a minute, which is quite a large fan. This box, because of size and constraints that we had, has a fan that's producing about 60 cubic foot a minute. So that means that we can run for short periods of time. We can't just leave it on and run it the whole time. We need to, because the temperature will exceed the temperature of the seals, of the glass to the anode and to other parts of the tube. So we have to run for a short period of time, and then we can have a rest, let the tube cool down, and then we can run again. So we will do it in those sequences. First of all, we just got it to the place where everything is sitting stably. Eric, if you want to start on, it should come on stably. High voltage. Okay, we just let that settle. Just slightly, check our plate grid currents. We don't want to overstress our tube. Okay, so we get a nice stable burning bush.
Ready for pulse?
And Eric, if you switch over to pulse. Okay, so now the whole nature of the discharge has changed. Before it was a burning bush, now it is basically a modulated, a keyed signal. What I'm going to do is I'm going to change the tuning in order to maximise the performance of what we get out of here. So as I'm reducing the tank capacitor, it's starting to become more aggressive. I'm going to make small adjustments to the grid. Increasing the primary capacitance, starting to sound less aggressive, softer, grid current's going up slightly, the size is going down, but now it's much quieter, much less aggressive. Start to maximise the curves. That's about right. So there we've got that's called the tree. So it's a tree part of the discharge. Eric has, when did you first see that, Eric, down in Santa Barbara, maybe?
Oh, this was in
Bolinas, okay. So it's rather nice to be seeing this again over after how many years?
Well, the last time I did this was at the Integratron.
Okay, that's a good 20 years ago.
Yeah, that's Santa Barbara.
Uh-huh.
Yeah, I was so a long time ago. That was 1988.
And you see this discharge is also starting to now show the characteristics of the Golden Dragon. So if we were to take some of these discharges and we were to fit that combination, that fractal pattern, which expands at the golden ratio, then we would start to get a good fit on some of these discharges. Okay, let's give the tube a rest.
Looking cool with the pulse width and speed.
Yes.
It's nice when they go pop, 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 pop.
Yeah,
pop, pop.
indeed.
Yeah, get them a little fatter. We can get it optimized.
And when it's running, if you a little bit louder.
Oh,
I just want to make sure.
Are you still recording?
It's going.
So, so just to summarise what we've shown you so far. So that kind of discharge was a result of having the cathode keying. So we started from the burning bush. Eric started the modulation at 20 cycles per second. We then got a much more of a kind of fractal type discharge pattern, and then we adjusted down in frequency to really emphasize the tree section. So where it starts to curve in and become what's known as the Golden Dragon discharge. And just to reiterate that is a fractal discharge which expands, the fractal pattern expands as the golden ratio. And I go into a lot of detail on that presentation in the conference that's just been, the Energy Science and Technology Conference in 2023. So if people that are interested in knowing more about the mathematics and that expansion, they can look into that presentation. So this is only the start of the demonstration. That's actually one specific effect that we can get. We're actually running at the lower parallel mode, so that would have been running at around about 2.5, 2.6 megacycles. We're just going to let the tube cool down a little bit, and then we're going to go the other way, up to higher frequency, see what that does to the discharge, and then we're going to start varying the modulation rate and the duty cycle of the modulation. Okay, so that was the first part of the demonstration. What we're going to do is we're going to put it straight back on into the cathode modulated, so we should get the same discharge as we previously showed, and then we're going to adjust the frequency the other way. So Eric, when you're ready with the high voltage.
Okay.
Okay, we just need to retune a little.
Let me put it back.
Just need to retune a little just to get it started. I will just soften that down a little bit, back where we were. Okay, so that's about the optimum grid leakage bias, that's down at this low frequency. So there is the tree. Now we're going to wind the other way in frequency. More aggressive. Starting to narrow in, the curves are starting to go. And this is known as the root. So one half was the tree, and now at the higher frequency, this is the root. I'll just explain what we did there. So we started off with the tree, which was much more curved, had the golden dragon. We increased, we reduced the capacitance in the primary using the tuning coil, so the frequency goes up. So we will be oscillating now at the upper parallel mode, that would be around about 3.2 megacycles, and we were readjusting a little bit on the grid leakage bias, and we can see that the whole discharge now, instead of being a rounded and more broad, it narrows down, it becomes longer, tendrils look much more like the root of the tree. So the branches of the tree at lower frequency and the root of the tree at higher frequency, combined with that kind of staccato type sound, much more aggressive, much more snappy.
What it is when you're in the root mode, you're in the dielectric energy, and when you're in the branch mode, you're in the magnetic.
Okay.
Because the power factor of the coil changes as you get off frequency.
Yeah.
So on the high end, it's a capacitor, and on the low end, it's an inductor. That's why the high end is so snappy, because it's dielectric.
Yeah. Yes, you've got that kind of like dielectric shock.
Yeah.
Whereas the magnetic, the rate of change of the magnetic field there is much more
Softer.
soft and smooth. Yeah. Good. Okay, so Eric, if you could turn back on again.
Okay, you're going to change the, what are you going to do next?
I'm going to set things back somewhere in the center.
Okay.
And then we're going to change the...
Okay.
Just going to soften that down a little bit. Okay, so we've softened it down. Now what we're going to do is we're going to change the repetition rate of the modulation in the cathode. So I'm going to go around. Jeremiah, can you take that? That's okay. this is starting to get hot, so we'll just let it cool down a little bit. So what we did there, just to recap, is we started off at the 20 cycles per second, and we reached, first of all, we reduced the width of the modulating pulse, so we made it narrower. So we reduced from 10% to 5%. So we made the transition sharper and narrower in proportion to the number of cycles that we've got.
Pulses.
Pulses
Per second.
Yes,
Yeah.
pulses per second. And that's, we see it narrowed down the discharge, it made it finer, it put more detail in there. And then we can increase the number of cycles per second up to 50 cycles per second. So we could hear it go up in steps as I went 20, 30, 40, 50. And then to finish, we just then increase the frequency, the center frequency slightly by adjusting the variable capacitor, and we just expanded it to an optimum size. Let's just have a look at that again, Eric.
We didn't lose our relays.
I hope so. Let's just slow down back to 20. Let's just slow this down a bit. Let me just increase the duty.
That's stuck.
Just put everything back to where we started. Okay, Eric?
Correct?
Yep. So, Eric, what do you think happened there?
Why did it?
Yeah, why did it?
Well, one of the relays probably stuck. You know,
Okay.
those relays are very fragile.
Okay, so just say a little bit about those relays. We haven't talked about them. They're special, aren't they?
Yeah, they're high-speed Mercury weighted reed relays.
Uh-huh.
They're basically, in the old days, they're those teletype relays. They refer digital teletype signals up to 100 words a minute.
Uh-huh.
They're very sensitive. They're telegraph relays, you know, some of the most sensitive relays in existence.
Okay, and what's the important part with it being mercury wetted? What is important
there's-
about that?
Sudden on, sudden off.
Uh-huh.
No bounce.
No bounce. Okay.
And no wear, because
Okay.
it's constantly replenished by the mercury.
Okay.
And these relays work pretty well up to 100 pulses per second, but I don't want to, you know, they weren't really designed for this, so
Yes.
I'm being careful with them because you can't get any more of them.
And how many have you got in there?
6.
Okay, so 6 joined in
So
parallel.
basically, a teletype circuit operates with an open circuit voltage of 120 volts
Uh-huh.
and a closed circuit maximum current of 100 milliamps. It's supposed to be 60, but it could get up to 100.
Uh-huh.
So that's basically how I'm looking at the relays.
Okay. Okay, and do you have to limit the plate current through those in any way? Or?
Well, you don't want to put too much current through them.
Okay.
And, you know, screw them up.
So
And you don't want too high of a voltage, otherwise, you know, they won't be able to interrupt the arc. So because they're in parallel, I have to have equalizing resistors.
okay.
Because if one closes just a little early,
Mm-hmm.
and then that's going to take the brunt of the current,
Yes, of
and
course.
that's not good. So the equalizing resistors tend to balance it out because they don't all close at exactly the same time. Then I have an inductive discharge dissipation, a capacitor resistor series that goes across the contacts, so any back EMF from any coils or what have you doesn't want to keep that arc going and damage the relay.
And those ballast resistors, they'll be in series with each of the relays.
contact.
Each
Yeah.
contact, yeah. And what would be the size of those ballast resistors?
Oh, I think
typically?
here they're like 22 ohms or
That's,
something.
so
So I
kind of
don't
low.
want any more back EMF than 10 volts on any of these tubes, otherwise it starts to act as cathode bias.
Okay. And then just to add, what we did to initially test that system was we first of all measured the open circuit cathode voltage to make sure that is not too much for the relays. So all that means is disconnecting one side of the cathode from ground and measuring that open circuit voltage on the cathode to ground, which we measured as with everything set as it would be when you were running. That measured at 158 volts. What is really the maximum that the relays can
I
take?
wouldn't go above 300.
Above 300.
Yeah.
Okay.
So this one's going to be a little harder because this isn't an oscillator, it's a power amplifier.
Yep.
So it's going to be getting constant excitation from the exciter,
Mm-hmm.
and that'll bring the cathode voltage up considerably. But the advantage is because that grid circuit's running all the time,
Yep.
is when you close the current path from the plate to the cathode, you get a better snap because the tube's ready to go.
Okay, so they're much crisper.
Yeah, but the expense is then you end up with more because the tube is acting like a rectifier for the driver.
Okay.
So whatever AC voltage the exciter puts out, that appears at the cathode as the output of the rectifier, that DC voltage.
Okay.
But I've never had any trouble in the past. So
Okay.
Yeah.
So per relay, it's about 300 volts max. What about 100 milliamps?
yeah,
Okay.
I would say that's their extreme.
Okay. So we are carefully adjusting the system to keep our plate current under 500 milliamps and our grid current under 100 milliamps. So that keeps the tube in the center of its characteristics, particularly as we have a lower airflow right here. Now, another significant issue in setting all of this up was when we were first testing, and we're going to go into this in detail because people might not be aware about some of the finer details of how to set up this kind of oscillator, this powerful oscillator. When we first turned on this circuit, we had ordinary wires connecting the tank circuit to the generator, so not insignificant. I mean, these were 12 gauge silicone coated microstranded wires, which are more than capable of handling what's going on here, but they can introduce parasitics, and we're going to go into that in more detail. And we noticed that because the fan, which actually does the cooling here, is connected to a small DC switch mode power supply, which is actually is located not that far from the anode. The anode is buried down inside this box here. And what we noticed is that when we turned it on and we couldn't strike the arc, that the fan stopped. So the fan stopped turning, and when we turned off the high voltage, the fan started again. So that was rather strange. Eric, do you want to go into more detail about why that is?
So what happened is basically you have to consider in these power circuits that all the connecting wires could possibly become a resonant circuit. So because there was two loops of wire going between the tube and the capacitor, the tube immediately thought the capacitor was a short circuit and used the loops of wire as a transmission line and oscillated at that frequency, which probably been about 150 megacycles.
Okay.
And this thing was screaming away at 150 megacycles, and without the fan alerting us to the problem, then we wouldn't have noticed, other than the thing wasn't working right, and it would have been. So anytime.
And just to ask, the 150 megacycles were obviously interfering with that switch mode power supply.
Yeah, because the higher the frequency, the more it wants to bite into things. Because
Okay.
the displacement current.
Yeah.
So there was all this RF amperage flowing off the plate of the tube and everything around it.
Okay. And that power supply just said no way.
Yeah, it
Stop.
just shut it off. So basically what we did is what I've always found is to use in the high, like here there's a coil of iron wire in the grid circuit.
And what's important about the iron there, Eric?
The iron eats up the electricity, high frequency.
Because what is the reason for that?
Well, because of its hysteresis, and the skin effect for iron is really serious.
Okay.
And it just that's why you can't use any iron hardware around your high power RF stuff.
So it's like a magnetic damper, it kind of
It's an impeder.
impeder.
Yeah.
Okay.
So that basically any high frequency oscillation is going to see this thing as a resistor and pretty much an open circuit, and it's just not going to.
So this kind of iron coil here basically is going to damp out all of the oscillations that might occur in that grid
prevent
connection.
them from getting going. Yeah.
Okay,
It's
and that will stop the tube
That's
from-
what's called a parasitic suppressor.
Okay.
So you have to have one of these in the grid, and you have to have one in the plate.
Now it's often referred that the parasitic compressor can be, for example, like a wire wound resistor with a choke wound
carbon
around it.
resistor with a choke wound around it.
Okay, and is that as good as the iron wire?
Well,
which
this is
better?
too powerful. It'll just burst into flames.
Okay, so you have to do this kind of
That's
thing
the
here.
way to do it.
Okay.
Yeah, that's from my experience.
Okay.
There used to be these things called glow bar resistors. What they were rods of carborundum that were doped in such a way that they have the right resistance.
Yes.
And those would be in series with the grid.
Okay. Good. And these connections here also iron wire.
Iron wire. Yeah, between the tube and what it connects to should be some kind of resistance wire.
Okay, so we stopped the whole thing oscillating.
And then the other thing is you have to make sure that all external connections to the tube are thoroughly bypassed.
Mm-hmm.
That
and
got
what's
rid
the
of
reason
most
for
of the
that?
parasitic oscillations right there is when they were thoroughly bypassed.
Okay, yes, that's right. Because first of all, we didn't have the iron wire. We just put the capacitor here at the input to the high voltage.
Another one here on the cathode.
Another one on the cathode, and also each of the meters.
Yeah, each of the meters has a capacitor across it because this is hot with RF. You don't want to burn these meters up. So all the meters used in any of these type of systems should always have a capacitor of roughly 0.01 microfarads connected across the terminal, short leads.
And that's a
Not
high
a
voltage
paper
capacitor?
It should be mica.
Okay, and that's a high voltage
Yeah, but
capacitor.
ceramic. It doesn't have to be high voltage.
Okay, what kind of voltage would
Whatever the meter is dealing with. So
Okay.
if it's a milliamp meter, then it does need to be more than 100 volts. If it's a 500 voltmeter, well then, obviously it has
Needs
to be
to be
higher.
more.
Yeah.
Yeah.
I just normally just use 1,000 volt everywhere.
Okay, so these RF currents, when they bypass, they just go straight down to the earth. Is that?
Well, on this case, yes. Well,
Yes.
but there's no earth here. There's just over here. So
Okay.
you have to think in terms of neutrals and and then the common point, which is then connected to earth. That's another thing. You can't just start connecting, this here, ground. Well, it doesn't work like that. There is no ground.
Yes. Okay.
You have 100 ohms of impedance between this and ground, maybe even more. It could be, if it's the right length electrically, there could be no conduction whatsoever. There's no such thing as ground, unless you got this. This is ground.
This is our kind of virtual ground
virtual
plane,
ground. Yeah.
which is also good because it actually all the flux that comes off the coil, instead of radiating out into space, it forms down the cavity down to the virtual ground plane.
And this is not connected to any other grounding system. It floats.
Correct.
That's what's important. Otherwise, you're transmitting, and then you're going to pump RF into everything.
Well, I'll just add a bit on that, because when we didn't have that and we were connecting back to the generator ground, then I believe, Eric, you were able to go and put a fluorescent bulb on the chassis, and it actually lights up.
Yeah.
What's the reason it lights up when you do
Because
that?
this thing is designed to transmit into the earth.
Okay, so it's basically transmitting lots and
Yeah,
lots
I mean, that's things that people don't realize. For one thing, is these parasitic oscillations. When they built the water-cooled tubes like I was showing you, the 858s and
Yes.
all those big ones,
Yep.
when they started hooking them in parallel, they started getting push-pull parasitic oscillations.
Uh-huh.
And in some tubes, it's almost impossible to get rid of that.
Okay.
And what happened was these things were putting out thousands and thousands, or tens of thousands of watts at very high frequencies, and it actually cooked some of the people working on the tubes.
Really?
We had no way to measure those frequencies back then,
Yes, of course.
and people were just all of a sudden, heating up and dying
So just because of
just
parasitic
because of the
oscillation.
parasitic oscillations.
What kind of frequencies are you talking
Well,
about?
that starts to become strange because some of these high transconductance Bell system tubes, double triodes like
Yeah.
the 5670,
Yep.
and I hooked them in parallel, and the scope, everything was fine on the scope, but every time I moved around, the plate milliamp meter was moving,
Okay.
and that's when you know.
you knew that
got
power was
trouble.
going somewhere.
But there was no frequency.
Uh-huh.
I've seen this before. There's no frequency. It's some weird. It's what's called a calitron.
So in that way,
It's called a calitron oscillation. It's like a multi-vibrator.
so
And
the body
frequency
is
can
actually
be-
absorbing that energy.
Yeah, the frequency could be thousands of megacycles a second.
Mhm.
So what you have to do is you have to unbalance the two tubes so they don't act push-pull. So
Uh-huh.
normally what you do is you put one of these parasitic pressures in one lead, and then you put another one in the other, but different. Or sometimes some manufacturers will just put resistor on one grid and not the other one at all. Or they'll use two equal ones. But it's best to do whatever you can to make sure that those two tubes are not perfectly equal and want to go into a calitron oscillation.
Mhm.
And a lot of amplifier designs don't pay attention to that kind of stuff.
Uh-huh.
And there might be something sneaky going on there,
Okay.
and it affects the fidelity of the amplifier, even though you can't see it on the scope.
And obviously, you managed to avoid absorbing too much of this
Well,
parasitic.
I didn't have the opportunity to be parallel connecting 858 water-cooled giant transmitting tubes, otherwise I could have cooked. But the thing is, I already knew about that, because I've been designing this stuff since I was 16 years old.
Okay, so we're going to do a second demonstration here where we're going to go through all of the effects that we've showed so far. So we're going to start from the burning bush, that's with no cathode modulation. Then we're going to go to cathode modulation, we're going to go up to higher frequency, we're going to go down to lower frequency. Lower frequency, we're going to see the tree. Higher frequency, we're going to see the roots, and then we're going to change some of the characteristics of the modulation. So just to be clear again, the center frequency of this at the lower mode is about 2.8 megacycles, and at the upper mode is about 3.2 megacycles, and we are on at the moment 10 pulses per second for the modulation.
So, yeah.
Well, that actually might be 20. If you look on the screen, Eric, does it say 10 or 20?
It says 20.
20. So we are on 20 pulses a second for the modulation. So, and we will just do a little bit of tuning to make sure everything's in the right place. So first of all, the burning bush, Eric, if you want to turn on, we'll just encourage that. We'll let it settle down. This is a tungsten carbide tip that we're using here. It's particularly good for the burning bush.
Ready?
And we look at, we've got 400 milliamp plate current, and we got about 60 milliamps grid current, average. Okay, when you're ready, Eric? So now we're going to go lower in frequency. It's quieter. We're going to adjust grid leakage bars just to maximize our discharge. That means that we're pushing the tube a little bit harder. Okay, so there we will be oscillating around about 2.6 megacycles at 10 pulses per second modulation. And we see we have the nice developed curves that we would expect from the tree section of the discharge, or the golden dragon section of the discharge. Go down to lower frequency, start to tail off. If this were a master oscillator driven, obviously we would have a wider frequency range that we would be able to work on. Because it's a power oscillator, we have a somewhat narrower frequency range. Okay, so that's the tree. I'm going to progress to a higher frequency. It's going to become, so on this side, this is on the magnetic side of the coil. So we're going to go to the dielectric side of the coil. Increase the capacitance, or reduce the capacitance, increase the frequency. Yeah, we'll cool down for a minute or two.
So let's go to 5 pulses per second.
Okay, so we're going to start directly in pulse mode.
Yeah.
Okay, off you go. Good. Okay, so this is 10. Let me just adjust a little bit. This is 10 cycles per second. Aaron, if you want to go to 20 cycles. Pulse per second.
Let's watch the dance. That's 9.
9, yeah.
I want to see the dance.
7, 6.
That's good right there. And you see which way it's turning, or what
Yeah,
the pattern
it was going this way.
It's not going back and forth. That could go a little faster.
Yeah, a little faster.
You can move the
fairway too and get a top view.
Oh, that would be interesting.
Yeah. Go a little faster.
Okay. 7.
Yeah.
That's it, right there is about.
Yeah, about there.
Yeah. There's some kind of pattern.
There is a sequence.
Yeah.
There is a choreographed sequence. There's something I talked about in my presentation as well on the Golden Dragon Discharge. There is a choreographed sequence.
Will it make it a little snappier than on the 5%
It is on 5 already. I can make it snappier.
Take it up a little bit.
That's now the root. Yeah, I think this needs to cool down a little bit. Yeah. Good. We'll just let this cool a little bit. Yeah, there is a choreographed pattern going on here.
Yeah, Aaron say if we get above it, maybe.
We roll this fairway and we can do a video from top view.
Let's try it. Yeah, why not? Let's try. Okay, when you're ready, Eric. Okay. Factor at the bottom.
Yeah.
It's almost like there's a bit of burning bush at the bottom.
Well, the pulse needs to be a little narrower.
We can make that.
Yeah. Right there. That's the threshold. So what? How many milliseconds is that? That's the threshold between burning bush and branch.
That is three cycles, 3%. So if you get it off the stove, yeah, actually get it off the stove.
The tube is broadening a little bit. It is on 10 milliseconds.
Let's,
Now it's that sound like some kind of capacitive discharge.
yeah.
It is.
It is capacity
Yeah.
discharge, yeah. We go to the other side.
Here. Take some photos.
This would be best done in complete darkness.
Yeah.
I thought all of this, like everything here.
It would actually be quite impressive in the dark.
Yeah. Maybe just a little narrower on the pulse. This is kind of light on the tube, so
Yeah.
we can go a little longer. Oh,
That's the lowest we can go,
Okay.
1%.
can you adjust the grid bias for some kind of maximum?
You tune it slightly then.
Interesting when it's slow like that, you can actually see. You know, we need a tip that keeps it in one. It's bursting forth from a number of places.
Yeah. Yeah, you want it on a very sharp point.
Yeah.
And we can put the other electrode in there.
Give that a
We
try.
stop it.
Yeah, let's give that a try.
Okay, give it a stop. Just let that cool for a little bit. And then I'll change the electrode tip.
See how it blackened the plate? It's not copper looking anymore.
That's the result of our cooling fan gave up during the demonstration
Yeah.
without us realizing it. That tube's probably up at around 250 C.
At least, remember like 500. Blacken it like that.
Well,
Looks like the tip of a soldering iron.
Well, it shows how robust these GU5Bs are.
Yeah.
That's normally a solid tube. It's do you have the heat gun? Does somebody have the? You have a heat camera. Yeah, 390. I'm going to have a look at this now. That's a very nice picture.
400 degrees.
Eric, come and have a look at this. You want to see?
Oh, yes, it looks very luminal. Looks like it's still lit up, doesn't it?
Yeah.
Really hot in there. Well, they must have that thing welded somehow, because when I did this when I was a kid, all the solder between the tube jacket and the plate and the radiator all spit out.
I think these are really, really
Yeah.
robustly designed tubes. They're perfect for this. It's sitting up about 390 Fahrenheit. What is that in centigrade? Is it?
That tube is, you know, it's not shiny anymore. burnt.
And it still works, so something to be said for the Russian GU5B.
Yeah.
It's good in the winter.
Yeah. Gather around the G25.
The GU5B.
Now we know how we're going to heat the water for the Tesla turbine.
Oh, now the fan started working.
Well,
Now the fan has started to come back.
It's trying.
Yeah, it's giving it its go. We're getting it at its best.
It's kind of moaning.
Sounds a little bit arthritic, I must say.
we got to change that. It sounds like a bug trapped in the windowsill.
Well, what was nice is now sitting here and not doing anything, and suddenly it starts going.
Yeah, well, and suddenly it stops. Something definitely was highly impaired.
Oh,
Yeah.
that was it.